Welcome to aminacademy.com. In physics, let us discuss about first law of thermodynamics. According to this law, some heat given to the system is used to change the internal energy while the rest is used in doing work by the system. It can be represented mathematically delta U equal delta Q minus W. Here, delta Q is the heat given or lost. Delta U is the change in internal energy. W is the work done. We can also represent the above equation as follows. The change in internal energy of the system is equal to the heat added to the system minus the work done by the system. Delta U, change in internal energy, equal to Q, heat added to the system, that is Q is positive, and work done by the system, W is negative. The first law of thermodynamics is a formulation of a law of conservation of energy adopted for thermodynamic process. A simple formulation is the total energy in a system remains constant, although it may be converted from one form to another. Another common phrasing is that energy can neither be created nor destroyed in a closed system. While there are many subtleties and implications that may be more precisely captured in more complex formulation, this is the essential principle of the first law. It distinguishes in principle two forms of energy transfer, heat and thermodynamic work, for a system of a constant amount of matter. The law also defines the internal energy of a system, an extensive property for taking account for the balance of energies in the system. The law of conservation of energy states that the total energy of any isolated system which cannot exchange energy or matter is constant. Energy can be transformed from one form to another but can be neither created nor destroyed. By the mass energy equivalence principle in Einstein's formula E equal to mc squared equation, matter and energy can be converted into one another without violating the first law. This is the context of a raster frame, a system observed from the same frame of reference. It takes relatively into account any reference frame differences such as relative motion needs to be accounted for. The first law of thermodynamic process is often formulated as like here. Next, further we'll discuss about the first law of thermodynamics. Now the system may go from one initial state to the final state in a number of ways. For example, to change the state of gas from P1 V1, that is pressure, initial volume, to P2 V2, that is final pressure, to final the stage 2 of pressure, stage 2 volume. We can first change the volume of the gas from V1 to V2, keeping its pressure constant. That is, we can first go to the state P1 V2, then change the pressure of the gas from P1 to P2, keeping constant volume to take the gas to P2 V2. That means we are from P1 V1 to reach P2 V2 in two ways. Alternatively, we can first keep the volume constant and then keep the pressure constant. Since U is internal energy is a state variable, delta U depends only on the initial and final states and not on the path taken by the gas to go from one to the another. Now we'll discuss about specific heat capacity. The specific heat capacity is defined as the quantity of a heat in joule absorbed per unit mass of kg of the material when its temperature increases 1 Kelvin or 1 degree Celsius and its units are joules per kg Kelvin or joules per kg per degree Celsius. Specific heat capacity is the amount of heat energy required to raise the temperature of a substance per unit of mass. The specific heat capacity of a material is a physical property. In SI units, specific heat capacity, that is symbol C we can write, is the amount of heat in joules required to raise 1 gram of a substance to 1 Kelvin. Further, a specific heat of water is 1 calorie per gram per degree Celsius is equal to 4.186 joules per gram per degree Celsius, which is the higher than any other common substance. As a result, water plays a very important role in temperature regulation because its specific heat capacity is very high. Next, we'll discuss about thermodynamic state variables and equation of the state. The state variable is defined as the variable which depends only on the initial and final state irrespective of the final state. Temperature, pressure, volume are examples of the state variables. Now we'll notice that thermodynamic state variables. What are they? Temperature T, pressure P, volume V, entropy S, enthalpy H, internal energy Q, mass M, density ρ. These are the state variables of thermodynamic. Equation of state. Equation of state is an equation that relates the value of pressure, volume and temperature of a given substance in thermodynamic equilibrium. That is relation between pressure, volume and temperature. In different form, that equation says the equation of state. The simplest known example of an equation of state is the one relation, the pressure P and volume V and the absolute temperature T of 1 mole of an ideal gas, that is an ideal gas law, PV equal to RT, where P is pressure, V is volume, is equal to RT, where R is the universal gas constant and T is the absolute temperature. Here, further, we'll discuss about the specific heat capacity of water. The old unit of heat was calorie. 1 calorie was earlier defined to be the amount of heat required to raise the temperature of 1 kg of water by 1 degree Celsius. With more precise measurements, it was found that the specific heat of a water varies slightly with temperature. For a precise definition of calorie, it was therefore necessary to specify the unit temperature interval. 1 calorie is defined to be the amount of heat required to raise the temperature of 1 kg of water from 14 degrees Celsius to 15.5 degrees Celsius. Since heat is just a form of energy, it is preferable to use the unit joule. SI unit of the specific heat capacity of water is 4186 joules per kg per Kelvin, which is equal to 4.186 joules per gram per Kelvin. Every equilibrium state of a thermodynamic system is completely described by specific value of some macroscopic variables, also called state variables. For example, an equilibrium state of a gas is completely specified by the values of pressure, volume, temperature, and mass, and composition of various mixture of gases. A thermodynamic system is not always in equilibrium. For example, a gas allowed to expand freely against vacuum is not an equilibrium state. During the rapid expansion, pressure of the gas may not be uniform throughout. Similarly, a mixture of gas undergoing an explosive chemical reaction, that means mixture of petrol vapor and air when ignited by a spark plug, is not an equilibrium state. Against its temperature and pressure are not uniform. Eventually, the gas attains a uniform temperature and gas and comes to thermal and mechanical equilibrium with its surroundings. So far we discussed about thermodynamic state variables, as well specific heat capacity and first law of thermodynamics in detail. We have done. Please subscribe our YouTube channel.